All right, so last Friday we finished up talking about intermolecular forces. And we said the first thing you should always do when you're looking at intermolecular forces is first determine whether or not the compound is covalent or ionic. And then if it's covalent, draw the Lewis structure and determine the three-dimensional shape. So let's take a look at the next one. We've got NH4OH. Is that going to be covalent or ionic? NH4OH? It's ionic. It's a little bit tricky, but one way of remembering this is we've got a polyatomic ion in there. That means that this must be ionic, which means that this is just going to be an ion-ion interaction. Whoops, let me rewrite this. Those ones are really easy. If you determine it's ionic, you can skip the shape portion. All right, next one, we've got C2H2. Is that ionic or covalent? It's going to be covalent. It has no metals in it, no polyatomic ion, so it's got to be covalent. All right, if we go ahead and draw this, we know it's got 2 carbons in there and 2 hydrogens, so I'll space these out. Let me write down covalent. Each of the carbons has 4 valence electrons, so we can pair those up. Say, all right, we must have bonds there. And then what about the remaining lone pairs on carbon? Yeah, it would have to be a triple bond, so we could draw it like that if we wanted to, or even clean it up and make it look nicer and show this as a cleaner triple bond in between. This is acetylene. It's that compound I talked about that's used in welding. All right, do you think this is polar or non-polar? Non-polar, right? Because if we look at it, it's symmetric. So even if it did have electronegative atoms, it has symmetry. That means it can't be polar. So this would be non-polar. And what would the main intermolecular force be if it's non-polar? Dispersion, exactly. So let's write that down. We've got dispersion for acetylene right there. All right, let's do the last two really quick. Where it says dimethyl ether and ethanol both have the same molecular formula of C2H6O, but they have very different boiling points. So let's draw the Lewis structure for both. And dimethyl ether is pretty easy if you haven't drawn it already. It's got 2 CH3 groups coming off each side of an oxygen. And then this oxygen has a lone pair versus the other one that has an OH coming off of it. It looks like this. So those are our 2 Lewis structures for both compounds. Same number of carbons, same hydrogens, same number of oxygens. Which one do you expect to have the higher boiling point and why? Does anybody want to throw out an educated guess? The one on the left. So you think this one would have the higher boiling point? It's important to remember that the strongest intermolecular force will have the highest boiling point, right? So which of these has the stronger intermolecular force? Let's first identify the main intermolecular force. So let's do this one over here. What's the main intermolecular force? Not everybody all at once. It would either be defined as dispersion, or if we think about the 3-dimensional shape here for this oxygen, what would the shape be? For the central oxygen. This would be bent, exactly. So most students in Chem 110 would say because it's bent, it doesn't have an equal distribution of electron density. So this would be dipole-dipole. However, it is a pretty non-polar compound. All right, what about this one over here on the right-hand side? What would the main intermolecular force be for this compound, ethanol? H bonding, exactly. This one, we definitely have a dipole, and we've got a hydrogen on the phone, so this one has H bonding. All right, so knowing the two intermolecular forces that are occurring here, which one should have the higher boiling point? Yeah, the one with hydrogen bonding, right? So ethanol, in this case, has the higher boiling point. So I'll just write higher BP due to stronger intermolecular force. Hydrogen bonding is stronger than dipole-dipole. Does that make sense? So some of these are tricky. Like I said, if you've got a covalent compound, it's always a good idea to draw out the Lewis structure, determine the shape, and determine whether or not it's polar, and double check that you have identified any hydrogen bonding if you have it. All right, we've got one last section, but were there any questions on this before we move on? No? All right, so let's pull up the new section. All right, so the last section in chapter 6 is all about forces in solution. And basically what this section talks about is what things dissolve other things. So how can we mix two substances together? And the general term I like to remember is like dissolves like. I use this in all of my chemistry courses. What I mean by this is that molecules with similar intermolecular forces will form homogeneous mixtures. What does it mean when I say homogeneous? It's evenly mixed, right? So unlike a pizza where you've got chunks of pineapple and whatnot on the top, a homogeneous mixture is evenly mixed. This is also referred to as miscible. Miscible is typically the term used for liquids that mix and don't form layers. Another thing to remember is if the IMF, or intermolecular force, of a solute is similar to a solvent they will mix. However, the opposite says if they have very different intermolecular forces, they will form layers. I'm going to try to emphasize layers here because that's the key feature, is if you have two things with intermolecular forces that are really, really different, they'll just separate out and form unique layers. So let's take an example of some items from our day-to-day life. Got a few. So in the first one, it looks like they're adding oil to gasoline. And if you think about both oil and gasoline, both have the similar molecular formula. They both are hydrocarbons, meaning they've got some amount of hydrogen, I'll call that X, and some amount of hydrogen, and I'll call that Y. What's the intermolecular force if we only have carbon and hydrogen? Are they going to be polar or nonpolar if there's just carbon and hydrogen? It's going to be very nonpolar, which means it's got to be what intermolecular force? Dispersion. So both have IMFs, or both have dispersion. And that means that oil and gasoline will mix. Which makes sense if you've ever had an outboard motor, or let's say a chainsaw, you have to mix oil and gasoline and it doesn't form layers, it mixes nicely. All right, the next one is oil and vinegar. You can see oil and vinegar form unique layers. You're probably familiar with that from salad dressing. And oil, is primarily a hydrocarbon, which, just like we said before, is HX or CXHY. Vinegar, on the other hand, is different. Vinegar looks like this. So let's take a look at oil. What was the intermolecular force for oil? Dispersion. All right, what about with vinegar? H bonding, right? So if vinegar has H bonding, that means they've got very, very different intermolecular forces. These will not mix. Does that make sense? And then the last one, we've got wine. And if you think about wine, wine is mostly water. So it's got a lot of water in there. Actually, let's draw it all out. What's the other thing that makes wine? What's the other main component in wine? Does anybody know? Grape juice that's been fermented into ethanol or alcohol, right? So ethanol is the fermentation byproduct of fermenting grapes. And it looks like this. And what's the main intermolecular force for water? H bonding, exactly. And what about with ethanol? Same. So they both have H bonding. That means that these will mix. Does that make sense? So typically, if they have pretty similar intermolecular forces, they will mix. But if they're radically different, meaning one's really polar and one's nonpolar, then they won't mix. There are some special cases, though. And I did want to show this because it does confuse students. Some ionic compounds will dissolve in solvents that can H bond. Oh. And the way that this happens is that the cation will essentially snuggle into the electronegative side. So for example, let's focus in on this cation up here. The oxygen's really electron rich. That means it'll snuggle up close to that cation and donate some of its electron density. Whereas with the anions, like I said before, then the hydrogens will donate, or will snuggle up against the anion, and then the anion will donate its electronegativity to those hydrogens. So this is an example of ion dipole. This isn't universally true that all ionic compounds will dissolve in water. So for example, if you take chalk, chalk is an ionic compound. If you throw it in water, it's really not that soluble. It won't evenly mix. But a lot of them will, like salt. Salt will mix evenly with water. There's also another weird example that hopefully everybody's very familiar with, soap. And I'm just going to call this soap is weird. Soap can dissolve both nonpolar and polar compounds. Which makes sense, right? Because if we're washing our hands with water, water's really polar, but let's say you get grease on your hands from cooking, you can wash that off with soap and it will dissolve in with the water. So what ends up happening is you have this green glob in here, so I'm just going to highlight that more. This green glob is oil. And on each of these soap chains, there's these little tails. I'm just going to highlight a few of them as red. That are nonpolar. And essentially what will happen is you'll encapsulate that oil droplet with a bunch of these red tails and form a big three-dimensional sphere. And then on the outside, right here, you've got polar heads. Like water. And that means that this entire capsule will dissolve in water. So soap is a really weird example of that. I like showing this because this is really similar to how cells behave. How many of you have heard about cell membranes? So cell membranes are really similar to this, where they have both a hydrophobic portion, meaning an area of the membrane that doesn't like water, and then a hydrophilic portion, meaning they want to face the outside towards the water end. So soap and membranes in cells are actually very similar. Does that make sense? All right, I've got a few review questions that I wanted to do, and then we've just got an in-class activity, because I know a lot of people wanted to practice stoichiometry and unit conversions again. So let's just do a few review questions. So the first one is the following characteristics. The following characteristics represent what type of compound? High melting point, crystalline structure, and soluble in water. Check with your neighbor and see if you agree. There's one we can rule out right away. We've never even talked about this. So, process of eliminate that one away. So now it's between covalent, molecular, or ionic. So let's check one. Let's just go with high melting point first. Do all covalent compounds have high melting points? No. Air, oxygen, O2, is a covalent compound, and it's a gas at room temperature. However, all ionic compounds, for the most part, have really high melting points. So that one helps us a lot. The other hint, too, is crystalline structure. Like I said, ionic compounds kind of pack in this three-dimensional lattice of cations and anions, and they end up forming what I call a brick wall. And so they're a lot more crystalline than covalent compounds that can flow around freely. So ionic would be the best answer here. Whoops. Does that make sense? All right, we'll do a few more. Which of the following will exhibit the intermolecular force of hydrogen bonding? A, B, C, D, or E? And how can we tell if something H bonds? Yeah, hydrogen's on the phone. Which of these has a hydrogen that's covalently bound to fluorine, oxygen, or nitrogen? Water. So that one's pretty easy. Let's do another one. Which of the following substances will be the least soluble in water? First of all, let's determine the IMF for water. We just said that was H bonding. So which of these is the least like H bonding? Let's go through and identify the IMFs for each of these. So A, sodium chloride, what would the IMF be for sodium chloride? Yeah, it'd be ion, ion. All right, what about B? What would the main intermolecular force be? H bonding. And we know that because we've got two hydrogens that are covalently bound to a fluorine, oxygen, or nitrogen. What about the next one, C6H6? Would have to be dispersion. Like I said, there's really no net dipole between carbon and hydrogen. So I'll just say dispersion. And what about NH3? H bonding, exactly. So we've got H bonding down here. All right. We want to find the one that's least soluble in water, so it shouldn't be like H bonding. So I'm just going to go ahead and cross out these ones. All right, and now we've got ion, ion, or dispersion. Which one's the least like H bonding? Dispersion, right? So for this one, nonpolar compounds really don't want to dissolve well in polar compounds. All right, ionic compounds, like I said before, sometimes will dissolve in H bonding solvents, so we do have to be aware of that. And we know that sodium chloride or salt does dissolve in water if you've done any cooking, so you can just use common sense there too. All right, a couple more. Oh, actually, I think that was it.